Morning everyone. Last week we have discussed about the water treatment, especially for the industry one, and we know we have two types of treatment. The first one is the external treatment and the second one is the internal treatment. First we will talk about the external treatment, and we can divide the external treatment into three. The first one is what we call as group A, and the second one is group B, and the third one is the group C. In group A, it's basically conducted to remove the non-suspended solid, and we have like sedimentation, then clarification and aeration. And now we will move to group B, water treatment system. The group B is the filtration system. So in the filtration, the aim is to remove the suspended solid by allowing the water through a porous layer. So the porous layer can be sand or anthracite or carbon, but actually this is so the filtration is not only conducted by using the porous layer, but we can also use another unit operation to do the filtration. Yeah, so let me change the slide first. Okay, so this is the filtration slide. So I believe you already have the filtration materials during your fluid mechanics class, I think last year, but maybe I will do some recap, a quick one on the filtration system. So this is basically the schematic diagram of filtration. In filtration, you will have a feed, and in this case the feed is a sludge, and then you will also have a filter. Yeah, a filter can be formed of anything. In the previous slide, it was said that the filter is porous material such as sand, but then actually you can have another material as the filter. Usually we can use like cloth and things like that. Yeah, so here you have the sludge, the feed, and then you push it through the filter, and then you can separate the filtrate and the what we call as this is the solid and then the filtrate. So in the sludge you have the solid part, and then what can go through the filter, we call it as the filtrate here. This is the filter. Yeah, so over time the solid will be accumulated on top of the filter and then form a very what is it, like a very solid part, what we call as cake. The filtration process can be categorized as conventional filtration and cross-flow filtration. The conventional one operate based on the dead end operation. Dead end means that you have the feed or the fluid go in this direction. Yeah, so basically this is your filter and this is your feed, and your feed go directly to the filter, and then all the solid will be retained by the filter, and then you will have the permeate or what we call as filtrate. The second one is cross-flow filtration. So in the cross-flow filtration, this is the filter, the gray one, and then you have your feed flow in this direction, in cross-flow tangential direction. Yeah, and by using some driving force, usually the driving force is pressure difference. Yeah, so you put a bit of slightly higher pressure on the feed, and then all the filtrate will go through the filter and separate it from the solid. Yeah, so what makes them different is in the conventional one, usually your cake thickness will increase over time, yeah, indefinitely. But in the cross-flow filtration, the cake thickness will increase in the beginning of the filtration, but then it will reach some constant value. Some constant value means that after certain cake thickness, the thickness will not further increase. Why? Because you have tangential flow here. When you have tangential flow, the cake on the filter can be removed by the flow itself. Yeah, so over time you will notice that the cake thickness is stable or constant. Yeah, and the second one is about the flux. Flux denotes the amount of filtrate that go through the filter divided by the filter cross-sectional area divided by the operational time. Okay, so when you have conventional filtration, because the cake on top of the filter uh, become more and more over time, the flux or the amount of permeate goes through the filter will will reduce over time. The different things happens in the cross flow filtration. So because your cake thickness in a certain time will reach certain constant value, same thing happens to your flux. So in the beginning of operation, your flux reduce, but then at some point of the operation, the flux become stable. Yeah, so um, as we can see here, yeah, in the beginning, maybe you can have higher flux by using dead end filtration. But if you want a more stable operation, you can choose the cross flow filtration. Yeah, but what we have in industry now is mostly the um, conventional one. uh, it will be different if you talk about membrane process. For the membrane process is a filtration system as well. But in membrane process, almost all the operation is conducted in cross flow mode. Yeah. Okay. And in the filtration system, we have two kinds of operation. The first one is the filtration when we use a constant constant pressure, and the second one is the filtration when we use constant flow. I will explain a bit about both of them. Okay, so in the case of we use constant pressure for filtrations, yeah, in the filtration system you need to put driving force. Yeah, so the driving force is usually the pressure difference between what, so the pressure difference between the filtrate or permeate and the feed. Yeah, so means that because the permeate or the filtrate is always on the atmospheric pressure, the feed pressure should be slightly higher. Yeah, you can put higher pressure than the atmospheric pressure for the feed. Yeah, so that's what we call as the driving force, the pressure difference. Okay, when we operate the filtration on constant pressure means that we put the value of feed pressure as constant. Yeah. Okay, so if I draw a graph for pressure and operational time, the graph will look like this. So no matter how long the how long the filtration has been operated, the pressure of the feed will remain constant. Will remain constant. Yeah. But then when I draw the graph about the permeate flow time versus the operational time, it will looks like this. Yeah, so over time the permeate flow, the permeate volumetric flow will reduce. Yeah, why? Because you remember, yeah, when we have filtration, we separate solid from the filtrate. Yeah, and then over time the solid will retain on top of the filter. When that happen, yeah, like let me go back. Okay, when this happen, when you have a lot of solids on top of the filter, the solid itself will have like will produce mass transfer resistance. Yeah, will produce mass transfer resistance. Yeah, it will retain the flow of the permeate through the filter. Yeah, in I think you can also relate this phenomena in real life situation when you have a water filter, or maybe when you try to get coconut milk from coconut flesh. Yeah, when you have a lot of solids, the permeate or the filtrate flow is not as high. Yeah, so this also happen in filtration. Yeah, basically, over time the solid on top of the filter will increase, and that will pose increase mass transfer resistance as well. Yeah, when we have constant driving force, to get the water out. Yeah, but then we have higher resistance, the permeate or the filtered flow will reduce over time. Yeah, so you have to expect this when you operate your filtration system. Yeah, so when you operate the filtration system in constant pressure, yeah, the reduction of permeate flow or the reduction of filtrate flow can be a sign that your filter is already has a lot of like solids, and then you need to wash it, and then you need to start the filtration operation all over again. Okay, the second operation is the filtration when you have a constant flow. So what we say as constant flow here is the constant flow of the filtrate. Yeah, so um, regardless the solid amount on top of the filter, you always want to have a constant filtrate rate. Yeah, so the implication of that is means that you need to increase your feed pressure over time. Yeah, so if I draw the graph, the permeate or the filtrate volumetric rate is constant over time. Yeah, but then you will need to increase your feed pressure over time. Yeah, in industry, this is the example of the filtration equipment. Here we can see the plate and frame filter. Yeah, so in the plate and frame filter, this is the frame, and you have a lot of plate here. It can start from 20 plates to even 100 plates or more. Yeah, so how it works, basically almost similar to what plate and filter heat exchanger works. Yeah, so you have a filter, you have the frame, the plate, and then you will have the feed go into the plate, and then you will put like cloth in between the plate, and the cake will be retained by the cloth. Yeah, so in this case, when usually this is operated at constant pressure. Yeah, so when you notice a reduced filtrate flow, you can disassemble the plate and frame filter, and then clean the cloth as the filter media, and then start over the filtration process again. This is another example. This is the vacuum filtration drum. Yeah, so in the vacuum filtration drum, you have your feet outside the drum. Yeah, you have the feet outside the drum, and the inside part of the drum will be connected to the vacuum pump. Yeah, vacuum system. So basically the outside pressure is the atmospheric pressure, your feet pressure is atmospheric, but then inside the drum the pressure will be less. Yeah, so this will force the filtrate to move from the feet outside to the inside of the tank. Yeah, so here you have the feed, and then suction from inside of the drum will make the filtrate move towards the inside of the drum, and then the solids will be retained at the outside part of the drum. Yeah, over time of course you will have more solids. Yeah, and then it will restrict your filtration process. But then because the drum um, rotating, yeah, rotating all the time, rotates all the time, um, the solid product can be removed by the knife over here. Yeah, so you have solid product, you have the solids here outside the drum, and because the drum rotates, the solid can be removed by the knife here. So in this part you will have clean drum again. Yeah, and then it moves continuously. Yeah, so basically that's filtration. ah, in our original slides, yeah, this is stated that the pressure drop is the driving force, and if the pressure drop reaches a certain value, the filter will be clogged or can be categorized as clogged. Yeah, you don't need to wait until the filter completely clogged. You don't need to wait until you have no filtrate at all to stop the filtration and clean the clog. Yeah, no. In practical application, usually you will stop the filtration system, yeah, when the filtrate is low enough. They usually, every industry has a certain value, has a certain standard, or when the pressure drop becomes high enough to reach a certain value as well. Yeah, so you don't need to wait until the filter completely clogged. Yeah. The example of filter equipment is the gravity filter, pressure filter, and the upflow filter. But what say in this slide is really conventional one. So this is the gravity filter. Consists of the sand. Yeah, here you have various sands. Yeah, and various stone with different size, and then you put it in certain way, and then you get the filter. Yeah, and this is the pressure filter. Basically this is almost similar with the gravity filter, but then you put pressure on the feet, yeah, by using the pump. Okay, this is the pressure filter, looks like this. So when using pressure filter, because you have higher driving force, mean that the operation can be conducted more quickly. Yeah, so the advantage when you use pressure filter, you will require less space, and then the installation is easy. But then it is very difficult to check the filter media because you need to open this filter. Yeah. And then backwashing. Backwashing is one method to clean the filter. Yeah, so the backwashing means that let me draw a bit here. Wait. Okay, so if I have the filter here, the feed conventionally, yeah, moves toward these directions, and here we got the filtrate, the water. Yeah. Over time, we will have a lot of solids here on top of the filter, and we want to clean the filter. Yeah, one method is by using backwashing. Backwashing means that we reverse the flow of the water. So in the backwashing, we flow the water in opposite direction. So we flow the water from this direction to here. Yeah, so the water flow can remove the solid suspended on the filter. Yeah, so that's what we call as backwashing. So that's one way to also clean the filter. But please notice that we need to use clean water to do the backwashing. Yeah. Okay, so this is the upflow sand filter. In the upflow sand filter, we have the sand inside this uh, conical tank. Yeah, this is the sand, and then this is the inlet. Yeah, oh sorry, this is the inlet. So the feed water comes through this way, and then flow through these holes. Yeah, there are several holes here where the feed water can flow through, and then the feed water will flow to this way, and the sand here will retain all the solids. Yeah, so at the end we will get the fresh water, or the clean water goes out from the conical tank. Okay, so that's filtration. The next one is the ion exchange. Yeah, so the ion exchange is resin. Yeah, it's the resin in soluble substances, usually in the granular form, like ball. Yeah, so in the ion exchange, occur the physical chemistry process. Yeah, so the separation in ion exchange is not based on the physical separation, but also on the chemical process as well. Yeah, so the resin, the ion exchange resin, can accept a certain positive or negative ions from the solution and release other ions. Yeah, for example, if we have like some ions on the water, such as calcium, or maybe, yeah, let's say we have a calcium chloride in the water. Yeah, so when we pass through the calcium chloride solution to cation exchange resin, yeah, the cation on the feed and the cation on the resin can be exchanged. Yeah, so if we have calcium as the cation on the feed, and here we have uh, hydrogen ions as the cation on the resin. Yeah, when the solution pass through the ion exchange resin, the resin will will bind the calcium and release the hydrogen ion. So now in the solution, instead of calcium chloride, we will have hydrogen chloride. Yeah, uh, the resin that exchange cation is called as cation exchange resin. And also to complete the reaction, we also have the anion exchange resin. In anion exchange resin, of course, we exchange the anions. Yeah, so for example, if the resin has the hydroxide ion as the anion, and in our solution we have a sulfate. Yeah, sulfate as the anion. When we pass through the feed solution to the resin, the hydroxide and the sulfate can be exchanged. Yeah, so now the resin will hold the sulfate ions, and in the solution we will have sodium hydroxide solutions. Yeah. Of course, over time, the resin can be saturated. Yeah, you can imagine that you have a resin here. It has several cations or several ions, and over time, after all the cations and all the anions is exchanged with other um, with those on our feet, the resin uh, is called as a saturated resin. Yeah, means that it cannot exchange anything with our feed again. Yeah, and when the exchange becomes saturated, it needs to be generated using acid or base solutions. Yeah, please visit this YouTube video to look at how ion exchange works. Now this is the example. Um, Here we have the cation exchange resin. Yeah, in the cation exchange resin, the calcium is exchanged by the sodium. So in the beginning, our resins contains sodium cations. In our feed, we have calcium and magnesium. Yeah, um, both of them. Yeah, basically all cations can be exchanged by cation exchange resin. So both calcium and magnesium can be exchanged by sodium. So now all the calcium and magnesium is binded to the resin, and the sodium is released to the feed. Now in the feed we have sodium ions. Yeah. Okay, this is the example of the resin particle. So the size is basically less than 1 millimeters. Yeah. Okay, the next one is the membrane in the wastewater in water treatment application. Um, so basically we have a lot of membranes type can be used in water treatment. But here I will explain about the most used membrane in water treatment. Yeah, so basically the most used membrane in water treatment is all the pressure based membrane. Yeah, the pressure based membrane is the membrane that operates based on pressure difference as a driving force. Yeah, it can be categorized into four. The first one is the microfiltration. The second one is the ultrafiltration, and the third one is the nanofiltration, and the last one is the reverse osmosis or RO. Yeah, so what is the difference between all of these membranes? Basically the difference is the pore size. Yeah, membrane is categorized as a filtration system, but it filter like micromolecule size. of particles. Yeah, so if we have sand or colloid, that's way too big for the membrane. Yeah, but if we have something small, for example, like bacteria, yeah, bacteria ions, that's suitable to be separated by a membrane. Yeah, so basically the difference between these four membranes, the pore size. For microfiltration, the pore size is around point, I think point 2, point 1 or point 2 until 1 micrometer. Yeah, so very small. And can the microfiltration can be used to separate everything that has a molecular size higher than zero point 0.1 micrometers. Yeah, it is very famous to be used to separate like bacteria, viruses, and also uh, big molecule such as carbohydrate, pectin, something like that. Yeah, and for the ultrafiltration, the molecule, the pore size is around um, point, wait, point 1, 0.01 micrometer until zero point 0.1 micrometer. Yeah, so the ultrafiltration can be used to separate like humic acid. Yeah, humic acid, please google what is humic acid, silicate, and also several ions. Yeah, because the pore size range is quite high. If we have uh, ultrafiltration with tight pore size, we can also use that to remove calcium and magnesium to certain extent. Yeah, and the third one is the nanofiltration. Yeah, is nano, so the pore size is in the nano size. Yeah, like 1 nanometer. Yeah, 1 nanometer. Yeah, it can be used to separate other things that is higher, that is bigger than 1 nanometers. And the last one is we have reverse osmosis. Reverse osmosis has even smaller pore size than nanofiltration, so um, because of the pores is so small, it always categorized as the dense membrane. Yeah, dense membrane, it is categorized as the membrane that has no pores. Yeah, even though if we do like scanning electron microscope, we can still see the pores of the reverse osmosis membrane, but only after we do the magnification until 20,000 times. Yeah, so because the pore is very small, RO is categorized as a dense membrane. Yeah. So the application of membrane in industry, the first one is to substitute coagulation and flocculation process. For this, usually we only use the microfiltration or ultrafiltration with a rather big pores. Yeah. For the filtration unit, this is depend on what you want to filter out. And the third one is for salt water production, means that you want to remove the calcium and you want to remove the magnesium. You can use ultrafiltration, but the rejection is not that good. Usually when you use ultrafiltration, you can reject 20 to 40% of calcium, magnesium, but you can also use nanofiltration. This one has a quite good rejection for calcium and magnesium. If you use a suitable one, you can reject up to 90% of calcium and magnesium. Yeah. And the last one is for demineralization. Demineralization means that you want to remove almost all of the ions, and here you can use reverse osmosis. So the size of the ions is different. Yeah, sodium has smaller ion size than the calcium and magnesium, and the reverse osmosis can reject around 99.5% of sodium. Yeah, so if you have a solution that contains sodium, the sodium can be rejected up to 99.5%. So for example, if you have like seawater, yeah, seawater contains around 35,000 milligrams per liter of sodium. When you have such rejection, please calculate how much sodium still be in the still occur still what is it, dissolve in the water. Yeah, please calculate. And for example, other example, if when you have like brackish water. Yeah, brackish water is air payau. Yeah, in brackish water usually the solid contains just around 5000 ppm. Yeah, if that all consists of salt, if because it's not all salts, you have also a lot of humic acid in brackish water. If it's all content of salt, particularly sodium, you can calculate how much salt remain. And for the lake water or the river water, you can also calculate how much salt that is remain when you use RO. So basically, this can be for the mineralization. This is the application of membrane treatment. Yeah, this is the pore size in micrometers. So basically, here is the pore size of microfiltration. Yeah, and you can look from this figure what can be removed by using microfiltration. Yeah, this is the size of ultrafiltration. This is the size of nanofiltration, the pore size of nanofiltration, and this one is close to RO. Yeah, so uh, you can examine what can be removed or rejected by a certain membrane. This is the example of membrane application. This is the UF system, yeah, ultrafiltration system in a textile company. Usually can be also used to treat the wastewater as well. Yeah, you know the textile company produce wastewater that's very dirty one, yeah, and cannot be directly uh, dibuang langsung gitu ya ke river. Itu can you can use that, you can do that. So means that you have to treat the wastewater first so you can pass the environment regulations. Yeah, one of the treatment can be used water filtration system. This is the ultrafiltration membrane in Indonesia Power Tanjung Perak as well. So this is to treat the water that will be further used to generate electricity. This is membrane configuration. Yeah, yeah. No need to talk much about this. This is the RO system. So the RO system is mostly used in Middle East, yeah, to treat the seawater into the potable water. Yeah, so because it can remove almost all the metals, it can remove almost all the ions in seawater. Yeah, but the drawback is the operation pressure of the RO is quite high. So for the RO to be operated in a good condition, you need to put feed uh, at high pressure around 40 to 80 bars. Yeah, so yeah, the pressure is high, but for the place where water is very scarce, this is still feasible. Yeah. Okay, the last one is for the internal treatment. So for the internal treatment, like I said last week, you add several chemicals, yeah, such as oxygen scavengers or the corrosion inhibitors into the water that already been treated before. Yeah, so this is like extra precaution. Yeah, so this is the objective. You can look at the objective. Please look at it closely, and this is the function of some chemicals for boiler treatment chemicals. Yeah, for boiler treatment for boiler water. Yeah, so you can add some alkalinity and pH control agents, scale inhibitors, sludge dispersant, oxygen scavengers, anti-foam, and corrosion inhibitor, and all. This is the example of the chemical use, and this is the function. Yeah, please look at it thoroughly, because yeah, this is all just data. Yeah, you need to read this all. Okay, I think that's all for now. We will continue again tomorrow at 2:30 p.m. Yes, see you in the class tomorrow. Thank you.